So your homework. On your homework, you were supposed to predict the shape of 3 molecules. One of those molecules was what I asked you to do on the quiz. Now, the steps were taught last Friday. They were recorded and placed on YouTube for you so you could review if you wanted to. They were reviewed yesterday. Then you were supposed to do the steps in your problems for homework last night. Okay? And so then I asked you on a quiz to do this. So, again, I hate to beat a dead horse here, but if you're doing what you should be doing in class, focusing and paying attention, and then trying to do the best you can on your homework, the likelihood is you're going to do well on things like quizzes or tests, because I'm trying to prepare you for those kind of things. Guys, I'm going over something now. Please pay attention. All right. So the first thing you do is come up with the electron dot formulas, and that's just that part for the nitrogen and this part for the hydrogen. And then the sharing arrangement is when you share electrons to get each of the atoms up to their highest possible number of electrons in their valence level. Hydrogens want to have 2 electrons like a helium. So by sharing this electron, this hydrogen now has not its original 1 electron, but now it has 2. And that's what it wants to be, like a noble gas. Nitrogen had 5 electrons, and when it shared 3 of those electrons with a hydrogen, it gave it 3 more, which gave it a valence level of 8. And most atoms want to have 8 electrons, and now it has a full valence. So it's like neon now. Okay, so it has what it would like to be as stable as possible. What you do with the next step is to do the Lewis dot formula, and for that you just squeeze everything together, and you get this shape. So the electrons that are shared here in this sharing arrangement with a circle around them get squeezed together. So when I squeeze atoms side to side, the electrons in the Lewis dot formula get squeezed over and under. And if I put the atoms over and under, the electrons get squeezed side to side like that. Okay, so there's a Lewis dot formula. You need to know that name, Lewis dot formula. Okay, then the next step is to start by predicting 3-dimensional shapes. To figure out the 3-dimensional shape, the first shape we do is called an electron pair shape. All you got to do is count the shared sets of electrons. All the sets of electrons around the central atom. So let me define what a set is. A set is all the electrons shared between 2 atoms. A set of electrons, when we're trying to figure out 3-dimensional shapes, a set of electrons is all the electrons between 2 atoms, shared between 2 atoms. Okay? Or lone pairs that are sitting by themselves. Alright? So this is a set because it's all the electrons shared between 2 atoms. In this case, this set has two atoms. This set has electrons. This set has 2 electrons. This set has 2 electrons. And the dots represent electrons in these dot formulas. This set has 2 electrons. And the lone pair is a set. So there's 4 sets of electrons around the central atom. Anytime you have 4 sets of electrons around the central atom, the 3-dimensional shape is going to start out being tetrahedral. And the electron pair shape just puts these 4 sets on the end of the arms of a tetrahedral. And it looks like this. What you want to do is to separate these out as far as they can get in 3 dimensions, not in 2 dimensions. And this may be difficult for some students to understand what 3-dimensional tetrahedrals look like. Okay? But this is spaced out as far as you can get them. And each one of these angles, every one of these angles, each angle to the next one is 109.5 degrees. Okay? Now, after you do this, and this has a name you need to know. It's called the electron pair shape. And you need to know the 3-dimensional shape, that is to say its geometry, and the geometry is tetrahedral. So taken all together, this is a tetrahedral electron pair shape. Houston, you have a question?
Yeah. Would you ever ask if, like on the test or anything, the degrees of the angle?
All right. Since I've taught it about 3 or 4 times now.
So how do
Okay.
you find the degree?
Well, you just know that a tetrahedral is 109.5 degrees. You just know it, because I've told you so many times. Okay? All right, now, then the next stage is to come up with what's called the modified electron pair shape. And for that, we look back here at the Lewis dot formula, find the shared sets of electrons, and replace the electron pairs in this drawing that are shared with the atomic symbol they're shared with, and put them there. Okay? So I have 3 shared sets here. So I'm going to replace those 3 shared sets with the atomic symbol they're shared with. So these right here are the shared ones I've made in this drawing, so I've just put 3 hydrogens on there. You could put on any one of the 3. I could have put the hydrogen up here and left the lone pair down here. Or the hydrogens, put this hydrogen up there and leave a lone pair down here. Doesn't really matter. Okay? You can put them on any one of the 4. Okay? As many as you need. The last thing then is to redraw this exact same drawing, exactly the same way, in pencil, and then erase lone pairs. So this part right here is going to be erased. Draw all this out again and erase it, and you get that. Now, if you don't do all those steps, and I've seen it happen over and over again, and I'm pleading with you to do it my way, because I've taught this a lot, and I know it happens, students will get to this part and will flatten it out, and it's not flat. Okay? If you don't know about that lone pair right there, if you leave out steps in this process, you'll get here and have the wrong shape. Okay? But if you follow the process carefully, you'll most likely get the right shape. Okay? Yes?
Do we make the lone pair the one that goes back and then take that out?
Again, it doesn't matter where the lone pair is on this thing.
It doesn't matter if that one
It could be the lone pair could be back here or here or here. Doesn't matter. As long as you have 3 hydrogens on 3 of those arms. Okay? Now, this is a tetrahedral. And the name of this right here, this is a tetrahedral electron pair shape. You need to know the name of it. It's a tetrahedral electron pair shape. This is a tetrahedral modified electron pair shape. You need to know that's what it is. Okay? And this is no longer a tetrahedral because a tetrahedral has 4 arms equally spaced. Does that make sense? Okay? So the name of this molecular shape, this is a molecular shape, but it's not a tetrahedral. It's called a trigonal pyramidal. Trigonal, T-R-I-G-O-N-A-L, trigonal pyramidal. Okay? Trigonal because there's 3 sides or 3 corners. And pyramidal because it looks like a trigonal because it's 3-cornered. Pyramidal because it looks like a 3-sided pyramid. See what I'm saying? Okay? Now, when we get to the balloon models, we're going to look back at this right here to kind of figure out what our balloon model is going to be. All this bonding here, all 4 of these bonds come from an sp3 set of hybridized orbitals, and there are 4 sp3 hybridized orbitals. Anytime you do covalent bonding, you have to hybridize orbitals. If you hybridize all 4 of the s and p orbitals, that's an sp3, and the shape of each of these orbitals is a single balloon shape, a party balloon all tied to the center. 4 hot party balloons all tied to the center. Okay? But once you share those electrons, the shape of that party balloon becomes kind of like a long balloon shape, like a Wiener shape. So each of these bonds here, because I've shared a hydrogen with it, becomes a Wiener shape. This remains as a party balloon shape, but each of these bonds, where I'm sharing just 2 electrons, becomes a Wiener shape. Okay? And the result is you get this, where each of the bonds between the hydrogen and nitrogen is a Wiener shape. Okay? We just leave a little ball on the end, a sphere on the end, for the hydrogen in our balloon model. Does that make sense?
Yeah.
All right. So that's how you get this balloon model for the ammonia molecule. The ammonia molecule is NH3, NH subscript 3. The difference between what's here and here, or we're showing the actual shape of the, in this case, the bonds, the Wiener shape bonds, or the lone pair has a shape like a single party balloon. We're showing the hydrogens, but the central nitrogen is not shown. The nitrogen's right there. We don't show the central atom in these balloon models. Are you with me? Any questions about that? And we didn't show it yesterday. When we're doing methane, we didn't show the central atom, carbon. Okay? When we did the sp3 hybrids, we didn't show the central atom. We just showed the hybrid orbitals. I'll get to that in a minute, okay? I got to do this right now. No, just hold on to it. Oh, you got to leave, don't you? Okay, hang on.
Every time that we do a hybrid, will it be a sp3?
What now?
Will all of our hybrids be sp3?
No, we're going to look at new kinds of hybrids today.
And are we making more balloon models?
We're making more balloon models. Hopefully. We'll see how far we get. Alright, so now, that was all about single bonding, guys. Yesterday we learned about single bonding. We learned that we can come up with the shape of molecules in a kind of stick drawing like this. Yesterday we made a stick drawing for methane. Last Friday we did a stick drawing for, what was it? Friday. One of the things you had to do for homework. Water was what we did last Friday. Okay? So those are the stick models. The stick models don't tell you everything. None of these models tell you everything. You've got to have lots of different kind of models to tell you everything. Okay? With methane, we had a hydrogen up. This was a carbon and a hydrogen up here. And we had 4 of these Wiener balloons. With water, we had 2 hydrogens. Oxygen's a central molecule, or central atom in the molecule. You have 2 hydrogens, okay, and 2 lone pairs. So water would have 2 Wiener shapes and 2 round balloons, okay? And then I asked you to do for homework hydrogen fluoride. And you have 1 Wiener shape for that and 3 party balloon shapes because you got 3 lone pairs around that fluorine. Okay? We'll try to get back to that later. Right now I want to go to what's called double bonding. Let's remind ourselves one thing about single bonding though, okay? Single bonding, which in each of those can be called a single bond, is the sharing of 2 electrons between 2 atoms. And usually, but not always, usually each atom supplies 1 electron for this bond. Sometimes both electrons in the bond come from 1 atom. Okay. But what I want to do is to go from where we learned about single bonding now to what's called double bonding. So once we have a bond, we call it a double bond. The process would be called double bonding. Okay? And so single bonding is the sharing of 2 electrons between 2 atoms. Double bonding is, yes, the sharing of 4 electrons between 2 atoms. So hopefully by tomorrow we'll get to triple bonding. How many electrons would that be? 6. Good. So what we want to do is look at formaldehyde. Okay, we're going to use that because it's a real simple molecule, but it has a double bond in it. Yes?
Single is 2 electrons and double is 4.
Correct. It's a Single, that's what it says right here. Single bonds have 2 electrons shared between 2 atoms. Double bonds share 4 electrons between 2 atoms. Okay? And formaldehyde has this formula. Okay? Or we could write it, if we wanted to, there's a lot of ways to write it. Okay? In fact, I could write it like that. But you don't need to know that right now. Yep. No. No. Carbon dioxide is way more complex than that. And we'll get to that. We'll be doing carbon dioxide in here. Okay? Alright, so number 1, this is for you to do now, okay? I want you to write the electron dot formula for all the atoms in formaldehyde. Write the electron dot formula for all the atoms in formaldehyde. Well, carbon monoxide is so much more complex, we won't even do it in this class. No. We won't be doing carbon monoxide in here at all. This is not carbon monoxide at all. Yes. Carbon monoxide is 1 carbon and 1 oxygen. And it has what a shared radical. And we're not going to get into that in here. Well, there's some similarities. But it's not this. It's a different structure. Okay? Alright, everybody doing this? Electron dot formulas for these atoms, please. All 4 of those atoms. Separately, yeah. Okay, don't try to do the sharing arrangement yet. We're going to do that together because that's where it starts to get kind of different. Alright, so if you have been following along and doing the work diligently and paying attention in class, starting with the last unit, Unit 2, we're going to do orbital notation and figure out how many electron dots there are on the outer layer and the valence level of an atom. You should know that a hydrogen has just 1 electron dot. Okay? And there are 2 hydrogens, so there's 2 hydrogens each with an electron dot, right? And then if you were paying attention and following along carefully, carbon is in the second row or period of the periodic table. The placement of lithium and beryllium here on the periodic table represents putting electrons in the second period or second primary energy level of an atom. And since these first 2 columns are the S sublevel region, it also means we're putting electrons in the S sublevel. So these electrons are 2s electrons. And over here where carbon is, we're going to put 2 electrons in the P sublevel region. And for carbon, it's in the second primary energy level, which means I have 4 electrons, 2s electrons and 2p electrons in the second primary level, so 4 electron dots. The outermost energy level is the valence level, we call it. Okay, all that sort of tying up together, all those concepts. And then oxygen, how many electron dots do I have around oxygen? 6. 1, 2. You put 1 on each of the 4 sides until you run out. If I only needed 2, I'd stop there. If I need 3, I'd stop here. For 4, I'd stop here. But I need more than 4. I need 6. So I'm going to put 2 more, so I'm going to pair up if needed. Okay, so that's the electron dot formula for oxygen. So number 1 is done. Okay, 1 and done. All right, we've got the electron dot formula for all the atoms. Now, number 2, we're going to combine these electron dot formulas into a single molecule using the sharing arrangement. Now you probably won't ever hear this term again, sharing arrangement, okay? Because nobody teaches it like this that I know of. They might somewhere. But that's a term you won't ever hear again. But it's going to help you a lot if you'll do it this way. If you take college chemistry, this is the step they don't teach in college chemistry, okay? It'll help you get there, okay? They'll teach you some more complex stuff in college chemistry, but it'll help you kind of figure out where to go. So the sharing arrangement means I want to share electrons between these atoms in such a way that each atom has all the electrons it'd like to have to be like the next highest noble gas. Okay? It's called the octet rule often, but then there's some atoms that don't want to have 8. They only want to have 2. Since hydrogen is in row 1, which is period 1 on the periodic table, its next highest noble gas is helium, which only has 2 electrons. And so it will have a full valence level when it only has 2 electrons. So I can share 2 electrons, or share an extra electron with the carbon here in order to get hydrogen up to 2, and share one here to get this hydrogen up to 2. And so both those hydrogens have all the electrons they can stand. Alright, we often say, using a personification phrase, we say they're happy now. Okay? Well now, that's great for the hydrogens. But the carbons need how many? 8. So carbon is right here. It wants to have all the electrons that neon has. Okay? It's upwardly mobile. It's trying to get like neon. Okay? I don't even know if y'all know what upwardly mobile means. Anyway, so carbon currently has 4 valence electrons and it wants to have 8. I just shared 2, which gave it 6. Okay? Well, at the same time, oxygen's right here. Already has 6. It also wants 8. They both want 2 more electrons than what I've given them so far. Okay? So I can share one here, but that would give the carbon and the oxygen just 7. That ain't enough. Okay? There's the double bond right there. Okay? So, by using a sharing arrangement, we can see how we can get all the atoms up to the number of electrons they'd like to have in covalent bonding. But this brings us to something new here, a double bond. And it doesn't look at all like a single bond. Okay? Now, the molecule that we draw out, the stick model we draw on paper, will look kind of like that. But we'll get there. We'll get to the balloon model shortly. All right? So, the next thing we want to do is we want to squeeze everything together. Into a Lewis dot formula. Okay? So if I have the carbon right here and I'm going to share these 2 electrons with this hydrogen, I'm going to snuggle this hydrogen up near the carbon, and that squeezes the electrons in between. If I have the atoms placed over and under, the electrons get squeezed so they're side to side. If I put the hydrogen out here on this side, this other hydrogen, and nestle it up next to that carbon, side to side, the electrons get squeezed till they're over and under. Okay? The oxygen over here, you're going to have 4 electrons in between. We're not going to put them 1, 2, 3, 4 vertically. Okay? The accepted way to write a double bond in this Lewis dot formula system is like this. Like the 4 corners of a box. Okay? Then the remaining electrons, now these are now called lone pairs. They just stay on the oxygen out there because they're not tied to anything. We're going to keep them there in this Lewis dot formula. Okay?
So you don't put one under the
You could. I could put them right here.
Well, no, instead of doing the box, because you put one under the
No. Then it's not, that's right, it's got to be shared between the carbon and the oxygen. That's true. Okay? Alright, so this then is the Lewis dot formula for this formaldehyde. Now, this hydrogen could be placed down below it here. Putting it over on the side is nothing special. Okay, I could move this one down below it. I could move the electron pair down here. Okay? What matters is that you have them paired up properly. Okay? In fact, a lot of times when people do this molecule, they'll have the hydrogen kind of over here, and this hydrogen that's right here, they'll have it down here like this, which is perfectly okay. And then with these electrons right here, which are like straight above it, over to here, and this set of electrons right here, down at this angle. Nothing wrong with those things, okay? I'm just trying to keep it a little bit simpler right now. In case you ever see something like that, you can move them around a little bit. It's okay. All right? Still pairs of electrons. Got it? And that's the way that Lewis designed the whole thing. All right. You like Lewis? Okay. Now we're going to get into three-dimensional shapes. To figure out three-dimensional shapes at this point in time in your chemistry career, we're only going to be looking at the shape around a central molecule. That's all we care about right now, is the shape around the central molecule. The central molecule is carbon. We don't even care about these lone pairs out here, okay, because they're not part of the shape around the central carbon. We're only looking at the shape that this bond forms, and this bond forms, and this bond forms. Okay? All right, so we're going to write what I call an electron pair shape. An electron pair shape is always a three-dimensional shape that gets electrons arranged such that the sets of electrons are as far apart as possible. We're going to get the three-dimensional shape that moves the sets of electrons as far apart as we can possibly get them in three-dimensional space. And remember, sets of electrons are all the electrons shared between two atoms. A set of electrons is all the electrons shared between two atoms. Okay? So a set of electrons is all the electrons shared between two atoms. Excuse me. Now, for the electron pair shape then, we want to get those sets of electrons as far apart as possible. How many sets are there in formaldehyde? Using this definition, how many sets of electrons are there in formaldehyde around that carbon? 3 sets. A set and a set, just like we've been doing before, but remember, a set is all the electrons shared between two atoms. And how many electrons are shared between carbon and oxygen? 4. So that makes up a set right there. So we got 3 sets now. Okay, that's a little bit different. Okay, when we're only doing single bonds and tetrahedrals and things, all the sets had 2 electrons. Now we got a new thing. Okay? What we want to do is arrange those 3 sets as far apart as we possibly can. So a tetrahedral ain't going to get it. We're in the South, that's why I can say ain't. A tetrahedral ain't going to get it. Why? Tetrahedral has how many arms? 4. How many do we need? 3. Got to chop an arm off of there. Okay? All right. So here's our central atom. And what kind of angle would get 3 arms as far apart as we possibly could get them? It's kind of a triangle, isn't it? Okay? We actually call it trigonal. And it sits on a flat surface. So it's not a pyramid because it's not on a flat surface. This is like we took that pyramidal shape we did with ammonia a while ago and just squished it like a fly. Okay? So this is a planar shape, right? It's on a plane. It's flat. Okay? So this is going to be called trigonal planar. Okay, that's the name of the shape. The three-dimensional name of the shape, the geometry of this thing is called trigonal planar. But we're going to write the electron pair shape. So this is going to be a trigonal planar electron pair shape when we're done. Yeah, there's a, in fact, that, let me think now, the carbon where the double bond O is in those amino acids, that's trigonal planar. Exactly what it is. Okay? All right. So I got to have 2 sets of electrons on these arms that have 2 electrons. But I have one set that's 4 electrons. And it doesn't matter which of the arms you put them on. Okay? Which arm do we want to put the double set on? Bottom right, she says. Anybody disagree with that? Want to fight over it? No, we're not going to really fight. You want to do the top? How many want the top? Raise your hand. How many want the side, right side? How many don't care? Oh, well, you don't care. All right. The top's one out of the people that voted. I'm sorry. So there's where we're going to put that 4 right there on the top. Okay? We're going to put these down here. And there's our trigonal planar electron pair shape for formaldehyde. And all these angles are the same. They're all 120 degrees. Now these are then, well, we'll get to the type of orbitals we have actually here, okay, in a minute. So all these are 120 degrees. All right. Sure. All right, so an electron pair shape arranges in 3-dimensional space all the sets of electrons as far apart as they can be. Okay? So we're trying to think in 3 dimensions. And Rika's athletes are really good at thinking in 3 dimensions because they have to think about side to side and up and down, especially if they're defensive backs, right, Rikas? Why don't you sit up and take some notes, Rikas? Work with us here, okay? All right, now.
What is that word after base?
All. How's that? Oh, why do they want to be apart? Oh, man. Oh, such a good question. Let's review. What's the charge on an electron? Negative. How do I get 2 electrons in the same orbital? Opposite spins, and it cancels what to make them allow them to be in the same orbital? Electromagnetic repulsion gets sort of canceled between them, okay? But I can only get 2 electrons in the same orbital. And they're still negative. We didn't change their charge. What do light-charged particles want to do? Get as far apart as they can get, hence the shape. Okay? All right. So now for the step number 5 then is to get to the next shape, which is to replace any shared sets of electrons with the atomic symbol for the atom with which they are shared. Okay, so we've got to go back and revisit the Lewis dot formula a minute. This set of 4 electrons is shared with oxygen. So on this shape, oxygen needs to go up here. Both these sets of electrons here are shared with hydrogens. So down here where I've only got 2 electrons, we've got to put hydrogens down here. So you should do this in pencil and put your 4 sets of electrons here, 2 sets of electrons, so that we're redrawing the exact same drawing. Exactly the same drawing. Then we're going to go and find the correct atomic symbol to replace as many shared sets of electrons as there are shared in the Lewis dot formula.
I have one question.
What's your question?
How come there's only 8 dots instead of 12?
Here?
Yeah. Take out the one from the O that was not.
We don't care about the ones around the O right now. Right now, all we care about is what's going on. When we get to three-dimensional shapes, all we care about is what's happening around that central atom, whatever that happens to be. Okay? So now we're going to replace the set of 4 with the symbol for oxygen. And we're still going to leave those lone pairs over here off of there. By the way, electrons that are unpaired like this are called unshared pairs. Unshared pairs are lone pairs. Okay? Yes?
Does it matter what the central atom is?
It doesn't matter in the sense that one atom is better than another. It's whatever the central atom is or whatever atom you're interested in as being the one you're kind of trying to figure out what those angles are.
So we could have put oxygen.
It's possible, but oxygen wouldn't work out. The only way to get this number of atoms together, 2 hydrogens and 1 carbon and 1 oxygen together, is to make it like this.
Yeah.
Nothing else will work out in the long run.
And didn't have enough for this.
Right, enough places to bond. Only carbon had enough places to bond to make it the central atom. Okay, that's one way to think about it. Very good. All right, and so the hydrogens have to go down here where the single set of electrons are located. Okay, so that is then our molecular shape.
How do you know that the oxygen is a double bond?
Huh?
How do you know that the oxygen is a double bond?
Because it's the only way to get both the carbon and the oxygen up to the point where they both can have 8 electrons and have this number of atoms.
The oxygen shares 2 electrons with the carbon.
Right.
I'm saying do not like write it in the last step any differently.
I'm not sure I understand what your question is.
Like the oxygen looks the same as the H's except it's different letters, right? But
There's the fact it doesn't matter. All we care about is what is the shape of all these angles right here. That's what we care about when we're doing this. Okay? Now, what's the geometry of this electron pair shape? Trigonal planar. Did we change the geometry? No. So this is also a trigonal planar. If we change the geometry, then we got to change the name. Okay? But now we do change the name. This is not an electron pair shape anymore because we've gotten rid of some of the electron pairs by replacing them with the atoms. And since we don't have any lone pairs left, don't have any electron pairs left, this is the molecular shape. If we still had some electron pairs out here, it would be the modified electron pair shape. But since all the electron pairs are taken care of here, this is now the molecular shape. Okay? So it's trigonal planar molecular shape for a formaldehyde molecule. All right. That's a lot of work. It's a lot to think about. Okay? And double bonds are kind of hard to think about. Okay? But we got to figure them out because we got to do it. All right? Now, so once we get that, then what we need to do is figure out what's going to happen with our balloon model. Well, something strange happens with balloon models. Okay, so we're talking about the balloon model, we're talking about the shape of the actual bonds themselves. Double bonds do not look like single bonds. Although one part of a double bond looks like a single bond. Okay? Double bonds form from the combining of both hybridized and unhybridized. Orbitals. Okay? So one of the two bonds in a double bond comes from hybridized orbitals, and one of the two bonds in a double bond comes from unhybridized orbitals. Okay? So we got to kind of go back and review from Unit 2 what we mean by all that. Okay? Alright. So carbon originally had an orbital notation of this. Okay? And when we hybridized carbon, when we made methane, we took all four of these S and P orbitals in the valence level and made them into sp3s. Okay? But now, we got to have some unhybridized orbitals. These are unhybridized. When we hybridized them, we combined them and made a whole new set of four, right? Yes? But now we're going to leave one of the P's alone and hybridize only two of the P's. Okay? So carbon then becomes this. Or its valence orbitals become this. One up, two, one down. Then we're going to combine 1, 2, 3 of the S and P's. We're going to leave one of the P's unhybridized. Okay. What did we call an orbital that hybridized the S and all three of the P's? What did we call the new orbitals when we hybridized the S and all three of the P's? sp3. I mean, we wrote it on our methane molecule. We wrote it over there on the hybridized orbitals over there. We did it this morning again when we did ammonia, right? All right. And the reason it's called sp3 is because you have one S and three P's mished together and made four new orbitals, all the same. Well, if I only use two P's and one S, what kind of orbital is that then? What? sp2. This is an sp2 hybridization. We take all the valence electrons and put one in each of the orbitals until we're done, and we're done with that one. Okay? With oxygen, we're going to hybridize it in exactly the same way. We're going to have we're going to have three orbitals that are called sp2s. And we have one p orbital that we're not going to mess with. But how many valence electrons does oxygen have? How many valence electrons does oxygen have? 6. So 1, 2, 3, 4, and then pair up as needed. Okay? So the shape of all this is going to be different, completely different now. Okay? Instead of having four orbitals that are all exactly the same, we're going to have one p orbital that's not changed. I didn't say pack up yet. Hold on. What is the shape of a p orbital that's not hybridized? We did this in the last unit. We made a model of p orbitals. What do they look like? A figure 8 or a double balloon, right? So this carbon's p orbital that's not hybridized is a double balloon. So that's the same kind of orbital we did when we were doing the unhybridized orbitals. Okay, so that's what this is right here. There's our p orbital. Okay? Oxygen does the same thing. We got a p orbital that's not hybridized. Okay? But now, what we have to do is to come up with three hybridized orbitals on both the carbon and the oxygen that'll try and be as far apart as they can be from this unhybridized orbital. Okay? And that's what we're going to start with tomorrow when we start doing our double bond. Bring more balloons tomorrow. Okay? More balloons.